Hello everyone, my name is Grigory Malinovsky. I'm a PhD student from King Abdullah University of Science and Technology. I'm going to tell about server-side stepsizes and sampling without replacement in federated learning. So this is joint work with Konstantin Mishchenko from Samsung KS Center and my supervisor, Peter Tarek from KAUST. So this is an approximate plan of my talk. I will give a brief introduction to federated learning optimization. I think most of you know what it is. And after that, I explain local SGD and federated random reshuffling method. After that, I'm going to introduce our new method, and I will consider two regimes, large and small server-side stepsize regimes. In the end, I will show some experimental results. Okay, let's get started. So federated learning is a general framework of distributed machine learning that enables training models across large number of heterogeneous devices. So federated learning has various applications from NLP to healthcare systems. So federated learning is a multidisciplinary field, and it could be studied from different aspects. In this talk, I'm going to focus on optimization aspects of federated learning. Okay, so we consider centralized distributed setting. In this setting, we have server and clients. So, and the process is the following. Server sends a global model to clients. Clients can update models using own data, and the updated models are transferred back to server. Server aggregates the updates, and this process repeats until convergence. So let's go to mathematical problem. So we consider standard finite sum optimization formulation. So where each loss function on client M, FM, is represented by another finite sum of n individual loss functions. And each FIM is individual loss based on data point on client M. So D is our number of total number of parameters, and capital M is number of clients. And small n is number of data points. For simplicity, we assume that each client has the same number of data points, but it could be relaxed easily. Okay, federated learning has a lot of characteristics. So local and global steps, data heterogeneity, partial participation, which means that only a small subset of clients can participate in communication round, communication compression techniques, also client heterogeneity, and data privacy. In this talk, I'm going to focus on first three aspects. Okay, let me briefly explain how local SGD and federated random reshuffling work. So in the beginning, on some round, we have a global model XT. This global model is sent to all participating clients. And each client starts to do some local steps. And after several steps, in my notation it's n, these updated models are transferred back to server, and server updates by simple averaging. In local SGD, local steps are steps of stochastic gradient descent, where data points are sampled uniformly from all possible data points. Instead, in random reshuffling, we first sample a permutation of data And using this permutation, we sequentially go through these indices. So which means each data point is used only once. So in our words, we use sampling without replacement. So this is the only difference in these two algorithms. Okay, several papers showed that federated random reshuffling has better dependence on number of communication rounds. So instead of 1 over t, we have 1 over t squared. But we have to pay by factor of n. But if t is larger than n, it's fine. In our work, we would like to improve further random reshuffling scheme. Okay, so now we introduce our method. So the first part of the process is exactly the same as in federated random reshuffling. So we have global model xt. This model is sent to clients. Clients update local models according to random reshuffling scheme. But in the end, instead of sending models back and doing simple averaging, firstly, we have weighted differences for each client. And after that, these differences are sent to server. Server aggregates. And after that, server performs additional gradient type step using different step size eta instead of gamma. So this scheme allows us to have more freedom, and I will show how it works in two specific regimes. So let us consider large server-side step size regime. So if we plug our definition of differences, we will see that our GTMs, our estimates, is just average of local gradients, but calculated in different points. If local step size goes to 0, this approximation will go to exact gradient. So if we do a little bit algebra, we will see that if server step size eta is larger than gamma n, where gamma is local step size, we will have, in some sense, interpolation. And we will have additional jump, which is indicated as a green line in my illustration. So roughly speaking, if we have small client step sizes gamma, we can control local variance. And if we have small local variance, we can have larger server-side step. And we can, in some sense, can emulate gradient type method with small variance. Okay, so let us consider strongly convex and L-smooth function and look at convergence bound. So we have exponentially fast decaying term, and we have several sources of errors. So we have variance of random reshuffling, and we have variance caused by sampling of clients. And if m is equal to c, c is number of communicate clients, it would be 0. And we have also client drift caused by local steps. And we can see that the variance is decoupled. So we have step size gamma squared for second and third part, and we have eta for the last one. So we have a good decoupling of our errors, which allow us to control different sources of variance. So the similar effect we have in also convex and non-convex cases. Okay, let us consider small server-side step-size regime. So we have the opposite behavior. So since we allow large client substep sizes, we have large variance. And in order to control this variance, we need to use small server-side step size. And in total, so our step would be a little bit smaller than if we just average 2 points. So this trick is also similar to trick used in look-ahead method in deep learning, but here we use it for distributed case. Okay, in strongly convex regime, we also have a nice decoupling of our step sizes. So we have gamma cubed here, which doesn't depend on alpha. Alpha is our fraction between eta and gamma n. And this decouple allows us to control variance caused by partial participation. So if we have a situation when variance of partial participation is quite large, it's better to use small server step size. Otherwise, it's better to use large one. Okay, let's go to experiments. So tuning two step sizes is quite complicated, and so here we go slightly beyond our theory, and we use adaptive step sizes. So we use adaptive step sizes for server step size, and we use decaying step size for client step size. And we see that our method, so we call here random reshuffling of two step sizes, so it performs also adaptive gradient method and simple random reshuffling method significantly. And we can see that our server step size jumps from low to high value. So adaptive scheme allow us to use both regime, like benefits of both regimes simultaneously. We also go beyond theory for deep learning experiment, and so instead of using two step sizes, we also use two types of steps. So for local steps, we use SGD, and for server-side step, we use Adam, just one Adam step. And we see that with this scheme significantly outperforms just optimally tuned SGD and SGD with decaying step size. Okay, in conclusion, I would like to mention that we propose a new method which combines random reshuffling two step sizes, and also it allows partial participation regime. We had convergence guarantees for different classes of functions, and we also analyzed two regimes, large and small server-side step size. And we have quite good performance for adaptive step sizes. Thank you.